Converting paths to words. A word is generated by following a path through the grid. Let's write some code to turn a path of positions into a word of letters. Here's the test. So this ensures that paths can be converted to words. We could create a grid with specific letters, but there's no need. We'll see an example of that later. For now, we'll create a random grid. The actual letters don't matter. We don't care if these are real words. We just care that we can turn a list of positions into a string of letters. We can access any letter in the grid by its position. For example, in this case, 0, 0. So our test checks that the path to word function returns the same strings we manually construct in the test. This test, of course, fails as there's no attribute path to word. So we will now go and create this function. It's a very straightforward single line function. It gets the list of letters for the positions in the path and then joins them into a string. The test will now pass. Now we get into searching. So given a grid and a list of words, we need to find the words in the grid. So here's the test. So we need to ensure that certain patterns can be found in a path. So for this test, we will create a mock grid so that we can control the letters. In this case, it's a 2x2 grid containing the letters A, B, C, and D. We also define a dictionary of 3 words. So AB, ABC, and EEE. 2 of those words are in the grid and should be found. 1 of those words is not in the grid and should not be found. In this case, we're using the assert true for all 3 of the words, but on the last word, the not there word, notice we've used a not in rather than in. So this test has failed because we have no search function. So now we create the search function. There's a lot going on in this function. It's a function that accepts a grid and a dictionary, so it matches the dependencies we identified early on when we were planning a solution. So we search through the paths to locate the words by matching strings to words in a dictionary. First we get the neighbours of every position in the grid, and then we get the paths list to capture all paths that form valid words. You might be wondering why we're storing words as paths rather than strings. The reason for this is that a letter could be repeated in the grid several times. If we had two letter A's and we saved a word with an A in it, how would we know which A it is? So now we do a doSearch function. The function is a little strange. It's perfectly valid to nest functions, and in this instance it's very handy. The doSearch function exists within the scope of the search function code. It can't be called directly. The doSearch function has access to the other variables defined within search, such as the paths list, which it can add to. The doSearch function can be called by the search function and can call itself recursively to build up paths. The search function starts a search by passing a single position to the doSearch. This is a path of one letter. The doSearch function converts whatever path it's given into a word and checks if it's in the dictionary. If the path makes a word, it's added to the paths list. Whether the path is a word or not, doSearch gets each of the neighbours of the last letter, checks to make sure that the neighbouring letter isn't already in the path, and then continues the searching from that letter. So doSearch could call itself 8 times for each starting position, and again for each of the various neighbours of each neighbour, and so on. For each position in the grid, we do a search and convert all the paths that make valid words into words and return them in a list. Recursion is a topic that strikes fear into the heart of many novice programmers, but it is actually a very simple and elegant concept. A recursive function or data structure is simply one that is defined in terms of itself. In this case, we want to search the neighbours or neighbours of positions. You can imagine a sort of tree-like search space. Trees or tree-like data structures are the classic example of where recursion simplifies everything. You can imagine a function that searches a tree. To do so, it must search multiple branches, but those branches are merely smaller trees. So the function can pass the branches it must search to itself so that they can be searched. The end result being that as those branches split and so on, all of those splits are automatically handled by the search function, treating each branch the same and searching its children. This test will now pass. Now we have a working search function. We want to use a large dictionary of words. So we can use a test to try loading a dictionary file and checking to see if it has contents. So we test that the getDictionary function returns a dictionary that has a length greater than 0. Notice the file name passed to the getDictionary function. That is a file containing a dictionary of words. You can find numerous word files on the internet. The bigger the list of words, the more words your boggle solver will find. Here we're using an example from Duke University in the US, bogwords.txt. First we create a new file in our Boggle project called words.txt. If we go to the bogwords.txt page here, we just copy and paste into our words.txt file. Now we create the get dictionary code. This loads the dictionary file into a list of words. You can see it creates them as uppercase. If we run the test now, of course it passes. Now that we have working code, it's a good chance to put everything into your local Git repository.